Okay, well, thank you very much, Nathaniel, and thank you for putting together this, what's going to be an awesome workshop. We look forward to it every year. And welcome to, I see that we have lots of international visitors. It's great to see you guys here, guys, men and women both, and I hope you enjoy yourself. And I've got a lot to cover, so I'm going to get right into it. Some of this stuff you're probably going to, is going to look familiar. Some of it is going to be slight modification of what you've seen already, because as we get closer to the actual hardware, we've had to make some accommodations, shall we say, to make sure that it'll actually work, which is kind of desirable. Okay. There we go. Okay, so what is the Tangerine SDR? Well, Tangerine is a modular open source hardware platform and software platform, and it was conceived by a request from Nathaniel about 2 years ago for some assistance in developing, or actually not necessarily developing, but identifying hardware that could be used in the scientific inquiries that he's pursuing, specifically the personal space weather station. And our first thought was that we would just look around and find some off-the-shelf hardware, and we would write some software, we would modify, or maybe modify the hardware a little bit, and we'd have a platform to use. Turns out what we found was nothing really did what we wanted it to do. So we came up with the idea of building our own platform, and it's really evolved a lot since then, but it's run by, like Nathaniel said, a group of volunteers. The hardware is led by Tapper, but with close collaboration with the scientists, because after all, we want to know what they want to measure, and we're trying to give them the best tool that we can, and without breaking the budget, so to speak. Okay, and then we just want to make sure that Nathaniel mentioned this, but we are supported by an NSF grant, several NSF grants, and also Amateur Radio Digital Communications is generously providing some funding for the prototypes that we're going to be building any minute now. So what are the features of the Tangerine SDR? Well, like Nathaniel mentioned, from 300 to 1,000, it's going to depend upon what kind of performance you want. For the personal space weather station, we're probably looking at a little bit on toward the higher end, because you need a GPS disciplined oscillator, which adds significantly to the cost. But all the hardware and all the software is open source, and we've tried to make it as modular as possible so that you can configure it and pick the features that you want without having to pay for things that you're not interested in. And we hope it advances the state of the radio art, since we're using the most modern technology. So it has 4 basic components: a data engine baseboard, which I call it the data engine. It has an FPGA on it. It's basically a motherboard that the other boards plug onto. The other boards being 2 slots for RF modules, and a slot for a clock module. And the last component doesn't actually plug onto the stack of boards, but it's the compute engine, or host computer, which is kind of what makes this a little bit different, because we talked about building an FPGA in with a built-in ARM processor, but it became obvious that when you can buy a Raspberry Pi for $35, it's not cost effective to try and build your own computer. And not only that, every year you get better and better performance. I mean, they're up to Raspberry Pi 4 now. Next year it'll be, who knows, it'll be a 5, maybe a 6. Maybe there are other computer boards that perform as well or better for less money. So basic tenet is, don't reinvent the wheel if you don't have to. So this is the block diagram, and you can see the Tangerine SDR isn't just the data engine and associated boards. It's the data engine and associated boards paired with a single board computer. So what are the features we have? Gigabit Ethernet direct sampling receiver. So our main, our primary communication with the stack is Ethernet. Initially, coverage from 100 kilohertz to 60 megahertz. And initially, we're going to be receive only, but we have 2 slots for RF boards, so we can do a transmitter board in the future, which is definitely planned. Web-based configuration interface. This is courtesy of the Raspberry Pi or whatever single board computer we use. That software will run on it, and it comes virtually for free. Just ask Bill. He's spent his lifetime developing this software, and he's going to have a demo of that later today. Multiple UD streams covering all bands from 160 to 6. And remember, this is a direct sampling radio, so these streams are simultaneous and covering all the frequency range up to 60 megahertz. We also have USB 3 and USB 2 simultaneous I/O for USB 2 for things like an RTL dongle. And USB 3 was something that we added just so we have an alternate high-speed interface from gigabit Ethernet. Okay, so this is a mechanical drawing of the mechanical. It's changed a little bit from earlier ones you might have seen. Over on the left, we have the clock module in green, plugs into an M.2 connector. This is the same connector that you use for SSDs, but of course, we're not using it for an SSD. We picked it because it's very high speed and it's very inexpensive. And then up here, we have in orange, it's a little hard to see, you have a Raspberry Pi hat, which we're going to support with a regular Raspberry Pi header connector. And then if you build a special board that's a little bit longer and plugs into our high-speed M.2 connector, you can implement a host of different options, different features on what we call a leaf board. You got to have catchy names, right? So, and then what you see in blue here is the RF modules are underneath the data engine. They are back behind it, and you can see at the top SMAs coming out for the antennas, and at the bottom the connectors that plug onto the data engine, which is the main board in the middle. Okay, it's going to have a Max 10 FPGA 50,000 logic elements. That's the largest member of the Max 10 family. Going to also have some SDRAM that's typically going to be used for a softcore processor that resides inside the FPGA to do housekeeping and manage the DMA engines and things like that. QSPI serial flash memory is going to be used for additional images for the FPGA as needed. And then serial EEPROM, pretty standard, and a micro SD card, and that will likely be used for field updates. Wide input voltage range, your HamSCI supply will run this. We put a 3-port switch on the board, so there's actually 2 external gigabit ports, which means that you can plug it onto your home network and you can plug it onto your host computer without having to add an external switch. Okay, so this is where we are right now. This is the preliminary layout, and you can see that the clock module down here has not been expanded out. There was no way we could fit all the parts on it, so it's actually expanded out with a notch cut out of it right over here to the edge of the FPGA, which is this big guy here. It's a 672-pin BGA, so lots of routing. Most of the routing goes down here to the 2 RF connectors below. And then up here in the upper right is the area for the leaf board or the Raspberry Pi hat, whichever you choose to put in there. And then along the left side is all the I/O, a dual stack of gigabit Ethernet ports, power connector in the upper left, USB 2 here, and the USB 3 is kind of hidden underneath the clock module because it's very low profile. So that's the preliminary placement. We may fudge things around a little bit as we get to routing it, but that's about where things are going to be. Future boards, maybe larger, faster FPGAs, more DRAM, maybe a real SSD. And the reason we pick gig E is because it scales very nicely to 10 gig E, 40 gig E, etc. So, but the idea is to keep the RF ports the same so that you can use the existing RF boards that you purchase when you initially buy this. And of course, there's going to be more than one RF board, which we're going to get to in a minute here. So speaking of RF modules, this is the first one that we're going to make. It's a dual channel 14-bit ADC at 122 megasamples. It's got an attenuator on board and a 20 dB amplifier on board. A fixed low-pass filter that you can remove if you so desire, if you want to do undersampling. And we added headers for a user-defined plug-in filter, and it can be either a filter or an amplifier, whatever you want to build on this small daughter card arrangement, and it's optional. But the idea is it gives the users plenty of things plenty of options to play with. I envision this thing being used for a lot more than just a baseband receiver. And this is 2 channels, and they're clock synchronous, so you can use this for diversity reception. And also on the data engine, if you plug 2 of these modules in, one into each of the RF module slots, you can actually end up with 4 channels that are phase coherent. This is a block diagram of the RX module that we're going to build. A little bit of an eye chart here, but it actually shows up much better on your screens than it would if it was live in person on a screen at the front of the room. And again, a lot of the stuff in this presentation is here for your perusal offline, because there's a lot of information here. Here is this board is actually completed. This is the assembly drawing for the RF module. And you can see the SMAs on the left, and what you don't see is underneath here on the right, on the back side of the board, is where the connector is for that plugs onto the data engine. So future RF modules, the first one we're going to make, of course, is the one I just talked about. Jonathan Rizzo is going to talk to you a little bit later about a VLF receiver module for very low frequency, below where our current RF module below the frequency range it covers. And then perhaps undersampling modules, or you've heard of Lime SDR and the 9361 from Analog Devices are RF subsystems on a chip. So perhaps an RF module with one of these parts on it would be sufficient, would be useful. And a special thanks to Tom McDermott, N5EG, for the RF module design. This design is his. Okay, we move on to the clock module. Clock module was designed to be separately plug-inable, separate module. The idea being that the level of purity, stability, phase noise, what performance you want out of your clock module is not going to be the same for everyone. So we made it a module so you can pick the performance level that you want. And currently the first one we're working on has these features. Uses a Raycon Ultra Stable TCXO, and it has a ZF9T GPS on board. This is a dual band GPS, so it allows you to do total electron content measurements. The only downside of this this lineup here is the GPS is just pushing $200 just for the GPS. So it's a pretty expensive solution. The performance you get for what you're going to pay for it is going to be outstanding, but not everyone may want that kind of performance. So we've actually built the board with the capacity to handle 3 different GPSs installed. So we'll have 3 different manufacturing options, and you get to pick which one you want to pay for, what performance level you want to pay for, I guess is the best way to put it. Okay, this is the block diagram of the clock module. This is the final design. This has gone through about 3 or 4 different iterations. John Ackerman, who is the designer of this module, will talk at length about this right after my talk here in just a few minutes. And this is the current layout of the clock module. This is much more concrete because this is actually in routing right now. So we pretty much decided, other than maybe juggling some of these parts, moving them over 1/10 of an inch or things like that, it's pretty much going to be this layout. And again, this goes along the left edge of the board. This is for an external GPS antenna, a 10 megahertz reference input, and a 1 PPS output. And John will tell you about a board that you can buy as soon as he designs it, of course, that this will plug into, that will allow you to use this as a lab standard for your ham shack in case you you're not that interested in having a data engine. You can still utilize this board to get very highly accurate clock signals from it. Okay, these are the 3 versions I talked about. High performance with the ZF9T, mid-grade with the Neo M8T, and I'm not sure we're going to produce this because this M9N doesn't really give us a PPS output, so it's not that useful. And John will tell you all about this coming up here in a few minutes. I wanted to talk a little bit about the leaf expansion board. So what we've done is the blue outline is the Raspberry Pi hat, which we are going to support, generally support them, but not necessarily everyone, because we only have a subset of the signals on this connector that the Raspberry Pi has. But it's intended to support things like the Grape, and actually Jonathan is talking about perhaps making the VLF receiver a leaf board rather than an RF module, because there'll be signals down here if you extend the board outline to include the M.2 connector that we have at the bottom, this has high-speed I/O, as opposed to the Raspberry Pi hat, which is mostly like I2C and GPIOs that are relatively low speed. So by extending the board down here, you end up with a much higher speed daughter card, if you will, or hat board, or as we call the leaf board. I'm not even going to dwell on this too much. I wanted to leave this in because this is a kind of a chart of our competition. It's a little bit misleading because there are a lot of features on these, and I didn't list every feature that all these different these boards have. So, but anyway, here's a list of similar boards. You can go to their websites, Google them, find out what all of the features are, and you can do a comparison if you are interested in that. Okay, so what can I use it for? I got about 4 minutes left here. I'd like to leave some time for questions, so I'm going to go pretty quickly through these. You've probably seen most of these slides before, but again, personal space weather station, that's our first target. Perhaps a Phase 4 satellite ground station might be another application with some undersampling. Academic uses to teach SDR and FPGA techniques. Again, we made this whole thing modular. So if you want to build a simple, inexpensive one for academic uses, or you want to build a high performance communications SDR for hams, you can do that. Just pick your parts. So this is similar to Nathaniel's slide, but this is what we're going to come out of the gate with. A magnetometer, dual channel receiver, GPS DO that I just talked about, the clock module, and then a client computer, which will be either a Raspberry Pi or an Odroid, or I think we've been working with both of those, a Pi 4 and an Odroid. Satellite ground station, kind of the same thing, except you do an LNB out here and down convert, and then you do an up conversion and a power amplifier at the dish. So it looks similar from our hardware point of view. For each of experimenter, you might want a higher performance 16-bit receiver, and you're going to want some kind of transmitter, and maybe this performance here will be similar to a Hermes board or a non-100. Or a low-cost one, you could take off the GPS DO completely and use an onboard oscillator. You don't get the performance, you get a lot more phase noise, a lot more jitter, but it's very inexpensive. And this is the slide that Nathaniel had. So, okay, so what can you do with it besides PSWS? Well, we figure that not everybody is a personal space weather station nut, so like all of us are here, right? So perhaps we have some targeted features toward hams. Like
2 minutes, Scotty.
Okay, thank you. Like a whisper monitor, FT8 monitor. Remember, we receive simultaneously on all bands, so we can monitor all bands for whisper beacons. We can monitor the FT8 frequencies on all bands at the same time. So Bill's going to show you in his demo later this afternoon some features that we have, like for instance, a notification via email. So you can put a call sign in, your buddy's call sign in, and if the radio hears that call sign on any of the frequency bands, it sends you an email, tells you where and when the station was heard. And again, Bill will give you a demo at 12:20 p.m. Eastern today. Okay, so just a little bit of blurb on Tapper's mission. We support digital radio development with R&D funding and early volume production. That's what this is going to be. We're going to be building prototypes in the next month or so. And then after that, you'll be able to buy this from the Tapper store. And another plug too, coming up in September, the Digital Communications Conference. If you like this, this is more a science-oriented conference. We're going to be more of a radio-oriented conference in Charlotte. And you can go to tapper.org and find more information on this. And that's all I have here. Sorry for the lightning whirlwind tour, but hopefully you got something out of it, and the slides are up on the web for you to look at.
Thank you so much, Scotty. I don't think we have any time for live voice questions, but I think, would you mind answering some of the questions in the chat?
I will be happy to do that.
So Scotty will answer questions in the chat, and also tomorrow during the iPoster session, we'll have the breakout rooms available. So there's a good chance you could actually talk to Scotty in person in a breakout room tomorrow afternoon. All right, thank you so much, Scotty. That was fantastic. I'm really I'm really happy with the progress on this. I'm excited to see the hardware come out.